Hi Chem 30. I said that I wasn't going to do any Blair Witch chemistry lessons, but I lied. It's way easier for me to do this stuff at home rather than having to deal with people at work. So I get a bit more uninterrupted work time. So I gave you guys a lecture on acid ionization constant earlier today. I'm going to finish that up looking at the base ionization constant. So I'm going to do a couple examples and I'm going to finish this section of the unit up. There's not too much more to go looking at ice tables with base ionization constant. A lot of the rules are the same. We just need to understand the relationship between Ka and Kb in relationship to Kw. So just a quick couple rules. Reminder with Bronsted-Lowry, the strongest possible base is OH negative. Ionic substances contain OH negative, right? I kind of already went over this with the acid ionization constant. We need to consider dissociation when we look at hydroxide, so we do need to consider mole ratios when we dissociate the ionic compounds in solution. We don't need to worry about that with hydronium because it ionizes. It doesn't exist before the acid is put into the water. I already talked about this. Same rules. So percent ionization for bases is the concentration of the hydroxide ion over the weak base times 100%. So that's very similar to, right, so this equation right here, which is very similar to the acid ionization constant, which is the concentration of hydronium produced over the weak acid present times 100%, right? And your weak bases and your weak acids will be your reactants, and we're looking at the percentage of the weak base or weak acid that ends up turning into hydroxide or hydronium. So we did a few examples like that with Ka, and I'm going to do that with Kb, and we're going to look at the relationship between the two of those. You still have a 5% rule, so the concentration of the weak base over the Kb in this case. If it's greater than 1,000, then you can use the 5% rule. Now, I put page 750 numbers 1 through 10 up on the board earlier today. It's in the previous Ka lecture as well, but those are all good practice problems to deal with Ka and Kb. Now, when you look at, so to find Kb is on your data booklet, okay? So what you're given in here is your Ka values. So if I look at oxalic acid, for example, Ka is 5.6 times 10 to the negative 2. Now, when I can solve for Kb indirectly, so I know that Kw equals Ka times Kb, okay? And I know that Kw equals 1.4 times 10 to the negative 14th. My Ka for oxalic acid, right from my data booklet, is 5.6 times 10 to the negative 2. And that's multiplied by Kb. So if I have the Ka, I can solve for the Kb. So it's there, it's just there indirectly. So when we solve for this, 5.6 times 10 to the negative 2 equals Kb. I'm just going to get my calculator real quickly here. Okay, so when we solve for the Kb, it's 1.0 times times 10 to the negative 14th divided by 5.6 times 10 to the negative 2. So I'm going to end up with a Kb value of 1.78 times 10 to the negative 13, and that equals my Kb. All right, so when we talk about strong acid over strong base, or strong base over strong acid, we're actually talking about the base ionization constant and the acid ionization constant. So as we look at our data booklet here, okay, when we look at the big 6 acids, they all have very large Kas, so they have negligible Kbs because they all make hydronium. But as we look on the top left-hand corner, right, so as we go down here, the Ka it starts off large and then gets weaker and weaker and weaker, okay? So that's where we get the acid over base or base over acid. So if we have a relatively large Ka, that means that we're going to have a pretty small Kb, and as the Ka value declines, the Kb value increases. So you can see down here, hydrogen phosphate, which is right by the hydroxide, it has a very, very weak Ka, so a very, very strong Kb. Okay, so when we look at acid over base or base over acid, products or reactants favored, we're actually looking at the relationship between Ka and Kb. Okay, so and remember that equilibrium always favors the weak side. So if we have a relatively stronger acid in solution, that means that its conjugate base will be quite weak. And as a result, the equilibrium would favor that. Okay, so we can determine Kas and Kbs, and whichever one has a larger value will be whichever one has a larger value, the Ka or the Kb, that will be the way the reactants tend to act, and the equilibrium will move away from the bigger value. So that's actually where we get that strong acid over strong base relationship, and that's going to address the whole Kb deal right now. So let me give you an example that's very, very similar to a redox table. And I'm just going to have to write this on the board. Okay, so I'm asking you to build an acid-base table from the following. This was going to be HA plus B negative makes HB plus A negative. And then I have HC plus D negative makes HD plus C negative. So this is just a general equation, right? The H indicates an acid, the negative ion indicates a conjugate base. And I have HD Okay, so this makes H, so build an acid-base table. Okay, now when we look at the reaction here, And this says reactants are favored. Okay, and then we have products favored. And then products favored. So this is very similar to a redox table. Now remember, when reactants are favored, you have base over acid. And when products are favored, you have acid over base. So we're going to make an acid-base table here. So for this one, I have B negative over HA. Right, so for that, so I know that if I have HA, HB is going to be above that. Okay, now products are favored here. So I know that HC is going to be over D negative. And this also says products are favored. So I know that HD will be above B negative. So the C is going to go above the D conjugate, and the D goes above the B. So that means HC will be at the top. Right, and then HD will be in the middle here. Okay, so very, very similar to a redox table. Remember, the base over the acid is when reactants are favored, and then the products are favored when the acid is over the base. And you would do this with you could easily do this with your acid-base table. Right, so very, very similar to the concept of a redox reaction. All right, so that's all looking at Ka and Kb relationships. Okay. My notes are all messed up now. Okay, so let's look at some base ionization constant questions. Let's start with making the equilibrium expression. Okay, so examples. Okay, so let's say we have NH3 and NHF. Ammonia and sodium fluoride. So, and the question is asking you to write the Okay, so write the Kb expression for these. So we know that ammonia is a base. So we're going to have ammonia reacts with water. Now, what the ammonia does is the ammonia is a proton acceptor. It's not a proton donor. Okay, so bases accept protons, right? So this ends up NH4 plus OH negative. So there's your equation. And when we write the Kb expression for this, Kb is going to equal the concentration of NH4 plus times OH negative over the concentration of the weak base, which is NH3. Okay, so there's your Kb expression for that. Now let's look at sodium fluoride. All right, so NaF, you have to do dissociation here. Okay, so this breaks up into Na plus and F negative. And what I can do from that, this is on my chart. That's not. So this is going to be F negative plus H2O makes HF plus OH negative. Okay, so my Kb is going to be HF times OH negative over F negative. Okay, so again, it's the same process. We're now using bases as proton acceptors and not proton donors. Okay? So I want to do the same thing that I did with Ka in class earlier today. So I want to show you some examples of calculating Kb from amount concentrations. Okay, so we want to calculate Kb from amount concentrations. All right, so first example is the pH of a 0.10 mole per liter NaNO2 solution is 7.63. Calculate the Kb and percent ionization. Okay. So the pH of a 0.10 mole per liter solution of NaNO2 is 7.63. calculate the Kb and the percent ionization. So here's the deal, right? It gave you pH rather than POH. So we do need to convert pH to POH. So that's going to be one of the things that we're going to need to focus on. So when we look at this, first and foremost, we need to dissociate the ions. So this is going to be NaNO2. And that ends up being Na plus NO2 negative. Okay. So we have to dissociate this, and now I can make an equation. So that is NO2 negative plus H2O makes HNO2 plus OH negative. Okay, so remember, the dissociation has not given me hydroxide yet, which is the calculator essentially of basicity or POH. So if I don't have OH negative in the equation, I have to dissociate and then make an equation. Okay, so ice table. The NO2 negative ion, because this is a 1-to-1 mole ratio, all right, is going to be 0.1 moles per liter. I don't worry about that, and this is 0 initially. Okay, so I have a pH. So what I need to do is convert this to POH. So that's going to equal 14 minus 7.63. And that is 6.37. So that's my POH. So I know that the concentration of POH is going to be 10 to the negative 6.37. And that's going to equal 4.26 times 10 to the negative 7 moles per liter. So that is my concentration of hydroxide once this solution has hit equilibrium. Okay. So, when I figure this out, OH negative is going to be plus 4.26 times 10 to the negative 7. And this is a 1-to-1 mole ratio. So that's going to be 4.26 times 10 to the negative 7. Water is not considered in the equilibrium because it's not aqueous. So this is going to be minus 4.26 times 10 to the negative 7. And 0.1 minus 4.26 times 10 to the negative 7 is going to be 0.09999. And then this is 4.26 times 10 to the negative 7 and 4.26 times 10 to the negative 7. Okay, so here's my ice table. And now we solve for Kb. So solve for Kb, so I converted pH to POH. So Kb is going to equal the concentration of Na plus over the concentration of Na2 negative, which are the products, divided by, sorry, I need to erase that. The concentration of HNO2 times hydroxide over NO2 negative. Okay, so that's my Kb. So at equilibrium, that's going to end up being 4.26 times 10 to the negative 7 squared moles per liter over 0.09999. So when I solve for that, my Kb is going to equal 1.8 times 10 to the negative 12. Okay, so that's Kb. All right, so remember I dissociated and then I created my base ionization equation. So B, let's do percent ionization. Okay, so percent ionization is going to be, that equals the concentration of the amount of hydroxide made over the concentration of the weak base times 100%. Okay, so my hydroxide ion concentration is 4.26 times 10 to the negative 7 over the concentration of the weak base, which is 0.1. And that's going to be times 100%. So my percent ionization ends up being 4.34 times 10 to the negative 4%. So barely any of it ionizes. Okay. So that's your first KB question. You can say hi to the dog. Okay. Let's do another one. Okay, sorry guys, I'm just putting the dog out. Okay, so again, calculate KB and calculate percent ionization. So this is example 2. So we've got sodium, okay, so this says the pH of a 0.15 mole per liter NaF solution is 8.2. And calculate Kb and percent ionization. Okay, so the pH is 8.2. All right, so we have sodium fluoride. So we need to dissociate it first. So NaF is going to equal Na plus F negative. I'm going to get rid of the sodium, and I'm going to use the fluorine in the base ionization equation. So this is going to end up being F negative plus H2O makes HF over OH negative. Okay, so ice table, we initially have 0.15 mole per liter of F negative, because this is a 1-to-1 mole ratio. Okay, that's initially 0 and 0. So I need to solve for, so I have a pH, so pH equals 8.2. pH equals 8.2. I need to find pOH. So pOH equals 14 minus 8.2. Okay, so pOH equals 14 minus 8.2. And that's going to give me a pOH of 5.8. Right, so I can solve for the concentration of OH negative, and that's going to be 10 to the negative 5.8. Okay, 10 to the negative 5.8.